In this video, we're going to extend the idea of hypothesis testing to testing two means, or paired data, or two proportions. Basically, what we're getting at is no longer we're just saying, does this mean match the population? Now we're answering the question of how do we compare two groups. We want to say, are these two groups the same, or is group 1 bigger, or is group 2 smaller? So there's a couple different contexts where we can do this. The first is if we are going to compare two means with a known population standard deviation. If we know the population standard deviation, we can get a lot more specific in how we answer the question. And that big question is, are the groups the same? Is there a difference between Running Start students and traditional students? Is there a difference between men and women? Is there a difference between those that received a treatment and those that did not receive a treatment? Are these groups the same, or are they different? That's the big question we're attempting to answer. And the way we're going to determine if they're different is we are going to subtract their two means. The mean of the first group minus the mean of the second group, and when we do, they should be normally distributed. If they're the same, they'll be normally distributed around 0 with a standard error that is the square root of the first standard deviation squared divided by its sample size plus the second standard deviation squared divided by its sample size. So if it's normally distributed, we should be able to calculate a z-score. And the z-score says, well, gee, if we take the difference in the means, x bar 1 minus x bar 2, and then normally we would subtract the difference in the hypothesized mean, but we're hypothesizing that they're the same, so there's no difference, divided by the standard error. And again, the standard error is that standard deviation of the distribution. So let's take a look at an example going through the hypothesis test process that we should be very familiar with right now. Let's say the mean time for two floor waxes are compared. And so we've got wax 1 and wax 2. Wax 1 was done on 20 floors, wax 2 was done on 25 floors. And the sample mean of those 20 floors, it took 3 hours to wax. And of the 25 floors with the second wax, it took 2.9 hours on average to wax. And we know the population standard deviation for each wax is 0.33 and 0.36 respectively. The question we're going to attempt to answer is, at the 5% significance level, is wax 1 does wax 1 last longer than wax 2? I mean, it seems like it's got a higher average, 3 compared to 2.9. Well, first we need to know, actually we should start with, always first, the null hypothesis is that the mean time for wax 1 is the same as the mean time for wax 2. The alternative hypothesis is what we're trying to prove is that the mean time for wax 1 is actually longer than the mean time for wax 2. And so when we calculate x1 bar minus x2 bar, it should be normally distributed around 0 because they're assumed to be the same. And then the square root of sigma 1 squared, that's the standard deviation, so that's sigma 1 and sigma 2, so 0.33 squared divided by the sample size, we have n1 and n2, the number of floors, plus n2 squared, 0.36 squared, divided by n2 is 25. So x1 minus x2 bar is normally distributed at 0, comma, and then we grab our calculator, square root of 0.33 squared divided by 20 plus 0.36 squared divided by 25 gives us 0.103. So now we're ready to calculate z. Z is the difference in our means. 3 minus 2.9 divided by my standard error, which is 1.03. So my z value is 0.97. Now that we have a z value, we're ready to go up to our table to find 0.97. Actually, before we do, we never drew our picture, so we make sure we're on the right side. So here they're equal. 0, mu1 minus mu2 over here, we want to be a positive value. So we want that area over there. The table, I could even label that, that's the 0.97 point. The table is going to give us the area inside. So 0.97 off the table, 0.97 is 3340. 0.3340. So if we want the area off to the right, we take 0.5 minus 0.3340, and we get 0.166. So our p-value is 0.166. 16% is much bigger than the acceptable 5%, so we will make a decision to fail to reject. In other words, there is insufficient evidence to suggest the two waxes have different mean times. So we fail to reject our hypothesis. Seems to suggest that there's no difference in mean time. So again, it's exactly the process that we saw before. The main difference is now we're subtracting the two means and we have a new formula for standard error. But once we know that's the formula to use, we're ready to go. Again, just like before though, most often you do not know the population standard deviation. That's not very realistic. So we're going to look at how we can compare two means with unknown standard deviations. Population, I should say. Population standard deviation. Because more often I just have my data from my study. Again, we're asking the same question, are the groups the same? Or are they different? And just like before when we did not know the standard deviation, we're going to have to use a t-test. And we're going to do it on the calculator, because tables for t-test are rather inconvenient. Again, t-test is the only one you should be doing on the calculator. The z-test you should be doing by hand using the table. On the calculator, what we're going to use is what is called the two-sample t-test. And we'll look at that here in just a minute. For now, we're going to look at the average time spent playing sports by gender being recorded in a table. So for girls and boys, the numbers surveyed, we surveyed 9 girls and 16 boys, and the average time was 2 hours for girls and 3.2 hours playing sports for boys. And the standard deviation for each group, for the girls it was the square root of 0.75, and for the boys it was 1. Because we do not know the standard deviation of the entire population, we have to use a t-test, and for that we're going to go to our calculators. On the calculator, the way we get to our test, again, you're going to hit the Stat button and scroll over to Test, just like we did before. The second option is a regular t-test, but the fourth option is a two-sample t-test, like we are working with in this problem. We're going to tell it that we are going to insert the statistics. X1, that's the average time of the first group, is 2. The standard deviation is the square root of 0.75. And the number in the first group is 9. X2, X bar 2, the average of the second group is 3.2. The standard deviation is 1. And the number in the second group is 16. Then it wants to know about our hypothesis test. So let's go ahead and build the hypothesis test here. We probably should have done the hypothesis test bit before we got to our calculator. So to ask the question, at the 5% significance level, is there a difference? Is there a difference in gender? So the null hypothesis is that there is not. The mean for the girls is equal to the mean for the boys. The alternative hypothesis is that there is a difference. The mean from the girls is different than the mean from the boys. And notice the question's not asking are the girls more, are the boys more, it's just asking are they the same or are they different. So we're going to say not equal to for our alternate hypothesis. So make sure on the calculator we select not equal to for our alternate hypothesis. Pooled. For our purposes, the pooled will always be no. No, we do not pool. And then calculate. And what we get is a t-value of negative 3.14 and a p-value of 0.0054. Let's record that, actually in a different color. The t-value that we came up with was negative 3.14, and the p-value that would happen by chance is 0.0054, which is much less than the 5% significance level, so our conclusion is yes. Our conclusion is to reject the null in favor of the alternate hypothesis. Or there is a difference in time spent playing sports by gender. Again, the process is very, very similar to if we had one mean that we were comparing. Here we're comparing two means, so we just run a different test, but the process is the same. Null hypothesis, alternate hypothesis, t-test, p-value, reject, or fail to reject. And just like before, we talked about proportions, so let's compare two proportions. And again, we're focusing on this question, are the two proportions the same? We can take a survey, public opinion poll, what percent approve of the president's job, what percent of males, what percent of females. Are they the same, or is there a difference between males and females in their perception of the president? We can take a look at baby boomers. What percent of baby boomers have a cell phone with text, a smartphone, and what percent of Generation X has a cell phone with texting and a smartphone? We can compare two proportions and ask that same question. Are they the same? Or is there a significant difference between the two groups? Before we get into the statistics of it, though, we need to know how to calculate what we call the pooled proportion. Notice proportions we pool, means we do not. The pooled proportion, we're going to say P sub C, the combined proportion, basically assumes there was no difference. So we take the number that's supported from group A plus the number in favor from group B, and divide it by the number that's supported from group A plus the number that's supported from group B, probably needing parentheses on the calculator to make sure it divides in the right order. So we get this pooled proportion that says there's no difference, here's the proportion of everybody. Not the two groups, but the proportion of everybody. Once we know that, PA minus PB will be normally distributed around 0. We assume there is no difference. With a standard error, that is the square root of the pooled proportion, 1 minus the pooled proportion, 1 over the first number of elements, plus 1 over the second number of elements. And once we identify that, we can find our z-value. Our z-value says, what is the proportion difference between group A and group B? And what should it be? Well, if they're the same, it should be 0. So minus 0 over the standard error. And again, the standard error is what we just calculated in the second half of that big guy. So let's do an example and see if we can compare two proportions and determine if there's a statistically significant difference between the groups. Two different medications for hives are tested. 20 out of 200 on medication A still had hives. "30 out of 180 on medication B still had hives." At the 1% significance level, is there a difference? So we should always start with our null hypothesis. The null hypothesis assumes there is no difference. The proportion of A is equal to the proportion of B. The alternate hypothesis, this time they're saying, alternatively, is there a difference? We don't care if one's bigger or smaller, we just want to know, is there a difference? So proportion A is not equal to proportion B. So what we're saying is 0, there's no difference. Is it going to be bigger or smaller? How much area is that? Notice this is a two-tailed test. We're going to have the probability occurring twice. So first, proportion A minus proportion B. Actually, we probably should know what the proportions are because they don't give them to us. Proportion A, group A is 20 out of 200. So that's 0.1. Proportion B is 30 out of 180. That's 0.167. The pooled proportion, the combined proportion, is 20 plus 30, all of them with hives, divided by all of them, 200 plus 180. Probably going to put parentheses on my calculator or adding them separately. When we do, we get 0.132. So, proportion A minus proportion B should be normally distributed around 0. There should be no difference because we assume the null hypothesis is true. The standard error is the square root of the pooled proportion, 0.132, times 1 minus 0.132, times 1 over the number in A. Group A had 200 people, plus 1 over the number in B. Group B had 180 people. So that's going to give us the square root of 0.132 times 1 minus 0.132 times 1 over 200 plus 1 over 180. Want to make sure on your calculator you know where to close your parentheses. When you type in your square root, make sure that you don't close the parentheses too soon. You want to take the square root of the whole thing. You know you've done it right if you've got 0.035 for the standard error. If you don't have 0.035, figure out what you might be doing wrong. Ask a classmate or your instructor. We're ready now, though, to find our z-value. Our z-value is the difference in proportions, 0.1 minus 0.167, divided by the standard error of 0.035. And so in two steps, 0.1 minus 0.167 is negative 0.067, divided by 0.035. We get negative 1.91. So we're at negative 1.91. from our table, 1.91. 1.91 is 4719. So the area is 0.4719, and when we subtract 0.5 minus that, we get 0.0281. But remember, with a two-tailed test, it's on both sides, 0.0281. So when we add those together to get our p-value, 0.0281 plus 0.0281, our p-value is 0.0562. And if you remember, we were testing at the 1% significance level. Well, this is 5.6%. So our decision is we will fail to reject the null hypothesis, because there is insufficient evidence to suggest there is a difference in treatment. Seems the difference in treatment might have just been by chance. Both Hives treatments seem to have the same proportion. Those are kind of the three tests that we saw in our previous chapter, back in chapter 9, where we were testing a single mean or a single proportion, whether or not we knew the standard deviation. Today we've extended it now to saying we have two means or two proportions. And depending on if we know the standard deviation, we might adjust from a z-test to a t-test. There is one other type of paired data, though. The stuff we've seen so far have been independent. One data result had no effect on the other. We had two groups, boys and girls, and we were comparing them. And what one boy said had no effect on what another girl said. There is one other type of two-sample test, two-group test, which are matched pairs or a paired sample. This is where we compare the results of twins. So one twin might affect the other. That's what we're looking at. Or we do a before and an after test. Before, we see how far you can run, then we do something to you, and then after, we see how far you can run. So the data values go together. Each data value comes in pairs, and they are matched. They are dependent. And so now we're looking at, is there a change? Before we were looking at, is there a difference? Here we're looking at, is there a change? Because we're looking at change, we are looking at subtracting the values. Which means there's not really two values we're running a statistic on. We're running a statistic on one thing. We are running a statistic on the difference. We are testing the difference. Which means we can use the methods that we saw in Chapter 9. We can do a single, probably t-test, if I can spell single, a single t-test, because we don't know the population standard deviation, on our calculator. For example, if a coach wants to know if a program can increase the weight lifted by his players. Some type of strength and conditioning program. I want to know if it made my players stronger. So we will compare before the program to after the program. So his first player before lifted 205 and after listed 295. Feeling pretty good. His second player lifted 241 before and after he lifted 252. Still feeling good. His third player lifted 338 before and only 330 after. Ooh, he went down. In fact, player 4 also went down from lifting 368 to lifting 360. At the 10% significance level, was the program effective? The null hypothesis is that the mean difference, because we're subtracting, the mean difference is 0. There is no difference before and after. The alternate hypothesis is that the mean difference is, and now we got to be careful here, which way are we going to subtract? If we do before minus after, we want the after to be bigger. So we're doing a small number minus a big number, ideally. If we do small minus big, we're going to end up with a negative value. So the difference, the alternate hypothesis, is that the mean difference will be less than 0. Let's take a look at how we can do this on our calculator. First, I'm going to enter our data onto the calculator. So I will hit Stat, Edit. We're going to clear out List 1, Enter. List 1, this is going to be our before data going across. Before is 205. Missed my 2. 205, enter. 241, enter. 338, enter. 338, I said. There we go. Enter. And the last one was 368. It's behind my calculator. Then I'll scroll over to list 2. List 2 is my after. 295. Enter. 252, if I can type it right. There we go. Enter. 330. Enter. And the fourth one was 360. Enter. What we want to test is the difference. And so the way we get the difference is we'll scroll over to L3 and actually scroll up so that L3 is highlighted. And we're going to tell it to subtract the before minus the after. L1 minus L2. To grab L1, we'll hit second, and number 1, we'll type in L1, minus second, and number 2, we'll type in L2. So we have L1 minus L2, and when I hit enter, it's going to fill in my chart with my data. The first one has a negative 90, the second one negative 11, the third is 8, and the fourth is 8. What do we subtract then? Now we're ready to actually run our t-test, and the calculator makes this really easy to do. How we're going to do this is, again, hit Stats, go over to Test, and this time we're going to do a simple t-test. The simple t-test because we're only looking at the difference, not the two samples, but just the difference. And instead of entering in the stats, we're going to tell the calculator to use the data Mu sub 0, we want that to equal 0. Our null hypothesis is that there's no difference. Enter. And then it's going to ask us what list the data should be in. The list, remember, was in L3. That's where we put our differences. So second 3, we'll type in L3. Frequency is always 1. Our alternate hypothesis is that we are less than the values. So let's select less than and have it calculate. Notice we end up with a t of negative 0.91 and a p of 0.2149. A t of negative 0.91, which involves a p-value of 0.21, I think it was 5. And we're interested in the 10% significance level, not a 21%. That's way too generous. So our conclusion, again, is going to be that we will fail to reject the null hypothesis. In other words, there is insufficient evidence to conclude the program had any effect on lifting. Yes, person 1 had a big increase, but he might have been an outlier. It wasn't statistically significant enough to conclude that there was any difference made by the program. So today, in this chapter, we're taking a look at comparing two groups. If we want to know, are they the same, we're going to do a difference. If we want to know is, has there been a change before and after or between the two groups, then we're going to look at a matched or paired sample. So take a look at the homework. We'll do some activities in class, and we will see you then.